Hello and welcome everyone to our webinar today on August 12th. It's great to have you join us. And I'm super excited to have Craig Just here to talk with some of the work he's been doing on anaerobic digestion, especially involving artificial intelligence and, more importantly, real-time measurements to try and help us manage digesters better. So I know that's a topic we're all excited about. If you have any questions during the webinar, feel free to type them in the chat and we'll make sure Craig has to answer them before we let him off the hook today. But otherwise, super excited to have Craig here to talk through some of the work he's been doing on anaerobic digestion for quite a while now.
Great. Hey, thanks for having me. It's fun to spend time with our awesome cyclone partners here in the middle of the state. Just for my sake, folks who are on, and I hope I can see the chat, but maybe we can yell some of it out. I'm kind of curious, like if you could throw it in the chat, who's a beginner, or are you beginner, intermediate, or expert at anaerobic digestion? I'd love to know the audience. Maybe Dan can help me out there too. And then I guess beyond that, when I say machine learning, uh, are you a novice? Are you an intermediate, or are you an expert? I would love to know who I'm talking to today.
On the first one, I did survey that when we started this program. And while we have some novices, we're mostly intermediates to a few advanced. I think with AI, I'm going to guess we're a lot more novice.
Perfect. Is that true, everybody? Oh, I see Jim Jordahl. I know him. Let's see. All right. Sounds good then. All right. Well, I'll make that assumption. I think I've got the right talk for this audience, and I've intentionally kept the webinar itself, the talk, pretty short. I love dialogue, so I would love to get some questions and different things like that going. So I titled this "Manure Meets Machine" because I know Dan deals a lot with manure. I've come at this with a little bit of manure experience, but a lot more experience in the municipal anaerobic digestion space. So I'll be telling a couple stories embedded together to get to the overall point here. And so, yeah, we're talking about reinventing anaerobic digestion with artificial intelligence. So, again, just to make sure we're all in the exact same space here. Perhaps some of you have seen this diagram. It's pretty popular out on the internet, originally put together by the EPA, I do believe. And so anaerobic digestion is our center point of discussion, but I do want to extend that to the concept of co-digestion, which you may or may not be familiar with, meaning co-digestion means some sort of hauled waste gets brought on site. For a manure digester, it might be that you bring in some organics from some food processing facilities in the area, so on and so forth. For municipal digesters, that would be the same thing. You're not just doing the municipal sludge, but you're bringing in some hauled organics. And those, again, can be industrial waste, could be from breweries, grease traps, food waste, so on and so forth. So there's some benefits to co-digestion. You get a potential boost in biomethane production. But there's a risk in the sense that you can have increased feedstock variability, and then you can get some digester upsets. And that's really at the heart of why the technology we've been expanding exists. So with a particular place in mind, beyond the technology, I'll be sharing a little bit of our work at Amana Farms. They have a manure digester there that also is taking in hauled organics, hauled waste, and so they are doing anaerobic co-digestion. And my experience with Amana Farms and anaerobic digestion does go a little bit deeper than just the technology that we'll be describing today, in the sense that we used some of their inoculum and some of their feedstocks to do a study on the impact of various organic loading rates. And so I want to make sure everyone understands the concept of organic loading rates, or OLR, in the context of anaerobic digestion. And the impact that that would then have on the microbiome, the microbiology that would be in those digesters, really with the goal of being able to have increasingly higher organic loading rates, because you can get more biomethane if you put more loading to the digester. But again, you've got some risk of digester upset if you do that. And so we studied those dynamics in the Amana Farms digester. With respect to machine learning, we did a project with Muscatine, Iowa. That's a water resource recovery facility, and I'll tell you more about that on the next slide. But the idea being is we took a bunch of their information that they had at that facility called SCADA, Supervisory Control and Data Acquisition time points, data points that they would have there. We analyzed those using supervised machine learning to be able to forecast biogas production, again, in this anaerobic co-digestion space. And so if you want to read a little bit more about what we've been doing in this space, feel free to take a look at those at another time. So here is where the bulk of our story in this space has originated in partnership with the Muscatine Water Resource Recovery Facility. I'll call that a WRF, a WRRF. And again, the emphasis here is that we've been doing full-scale deployments of what we call diffuse reflectance spectroscopy. I'll tell you what that is in a bit. And that's been a major focus of our research team. This particular facility, Muscatine, Iowa, about 24,000 people, 5.5 million gallons per day, average daily flow. For those wastewater people on the webinar, they have trickling filters and activated sludge, and then they've got 2 anaerobic digesters. If I can make a little cursor here, I don't know if you can see that way up here. There's 2 digesters way in the top with the white floating lids at this facility. So this facility receives a variety of hauled waste. So in addition to the sludge that gets generated at the facility itself when it's treating your flushes or at least the flushes from the community of Muscatine, they're hauling in a bunch of waste from companies like Nestle Purina, Kraft Heinz, Conagra, West Liberty Foods. They also receive pre-consumer deli waste from Hy-Vee grocery stores. We'll call this stuff as it comes in a variety of formats in cans and boxes, in containers. That gets depackaged with an industrial depackaging machine. I think I've got a picture of that here in a second. And then the kind of the slurry that comes out of that often looks like this stuff over here in the bottom right-hand corner, kind of this red stuff. Sometimes it's kind of a creamy color or whatever color that is. It's gross and it smells kind of funny. And but we call this high strength waste because, you know, pound per pound or gallon per gallon, it has a very high organic content to that. And so again, it's appealing to bring that stuff on site, put it in your digester and make some biomethane, but it's like rocket fuel and you have to dose it carefully. And they could get a huge pallet load of dog biscuits one day, a huge pallet load or truckload of Oscar Mayer sausage the next day. They're really trying to find out how best to put this high strength waste in each and every day, not only the amount, but then what composition of the feedstocks that they have on hand should they put together that day to then add into their digester. This is a picture of the large depackaging machine. They can throw boxes and cans and everything in. They get ground up in this kind of this cylinder right here that has just a bunch of rotating teeth inside of it. The organics fall out into the bottom here as a slurry, and then the trash then goes up this conveyor and then falls into a hopper and ends up getting landfilled. They put the slurry then into a tanker truck and they move it from this particular facility where this machine is located over then to the WRF. If we've got folks here who understand COD, carbonaceous oxygen demand, this would have a COD value greater than 150,000 milligrams per liter. If you aren't familiar with that number, that's a big number if you don't know what COD is. Volatile fatty acids, over 20,000 milligram per liter. And then typically a pretty high fat content, approaching 35%. If they don't put that in the digester in the right way on any given day, they can get a digester that's going to throw up. And that's what this digester did. If in the background here you can see this nice light tan color, that's what the side of this digester used to look like before it threw up on itself. And so there used to be a floating lid way up here. That floating lid is collapsed into the tank and is sitting now on top of the liquid in the tank. The biogas isn't being produced anymore. This digester has totally failed. And so what you're seeing here is the risk reward. The risk is 100% digester failure and no biomethane. The reward is adding this, digester rocket fuel in the form of this high strength waste and getting a bunch of extra biomethane. You got to try to balance those two. And it's really difficult on a day by day, candidly, an hour by hour basis to provide some information to the operators such that they can make the decisions needed to maximize that biomethane production and minimize this risk of catastrophic failure. So, given that, my solution, or at least my team's solution to that issue, is something called diffuse reflectance spectroscopy. It's a fancy name for shining infrared light into the slurry and then seeing what reflects back as a bit of a fingerprint then for what would be the composition of any given slurry. And so we've been working with a company called Buki. They make these very fancy stainless steel versions of these sensors that are used very commonly in food and beverage industries to keep your beverage, right perfectly within spec as they're trying to make that so they can use that as quality control. When we hook this sensor up to a pipe that contains high strength waste or even digestate that's in the reactor, we get these squiggly lines over here, right? We get a bunch of squiggly lines, and the amplitude of those squiggly lines change as a function of the composition of the slurry. All right. And so the promise is that then we could use these supervised machine learning techniques to turn these squiggly lines into predictions of the composition of the feedstock and or the digestate. That's really where machine learning, this sensor, and then really the challenge I've posed in front of you, that's where these things all converge. So what it looked like in real life in the basement, right by those anaerobic digesters in Muscatine, is we put this sensor on a cart that also had a peristaltic pump. Some people would call this like a kidney loop, meaning we had a 4-inch pipe that fed the high strength waste into the digester. On that 4-inch pipe was a 1.5-inch, a tiny nipple that we could draw some of that high strength waste out of, and then slightly down pipe, I guess, or downstream was another 1.5-inch nipple where we could just put it right back into that original pipe. So we're siphoning a little bit out of the main flow, running it through this sensor that's on this cart, and then putting it right back where it came from, both for the high strength waste feed and for the digestate in just one of those digesters, right? We did the study in one of the digesters. So how did it work? Okay, so let me show you what you're seeing here. See if we can get oriented. First and foremost, volatile solids. So your volatile solids loading rate, volatile solids is a bulk measure of your organics. You don't really know the composition of it when you measure volatile solids. You don't know what types of organics are there necessarily, but you just know that they're, likely readily degradable because they're in that volatile solids fraction of the solids that might be in your slurry. And so here we're using diffuse reflectance spectroscopy to provide a real-time high-strength waste composition for volatile solids. And so what we did was we collected grab samples between January and June. I believe this is in 2023. And the blue line is what we predict from the diffuse reflectance spectroscopy technique coupled with machine learning. So it makes a prediction on what it thinks volatile solids is in milligrams per liter. And then all of these symbols, all right, if it's a circle, that means that's the data, that's the grab sample we use to train the model. That's where it fell on that particular day. All the triangles are all the testing data that were also collected that we use to evaluate the effectiveness of the model. How good is the model, so to speak? And so we've got training, testing, and predicted data there as a time series. It's nice to look at it as a time series, but it's much more simple to look at it as a condensed one-to-one plot. And that's what's over here on the right-hand side. We've got observed volatile solids from our grab sample data on the x-axis, and then we've got predicted volatile solids on the y-axis. In a perfect world, all of these data points, all these circles and triangles would land perfectly on that one-to-one line that's at a 45-degree angle right there. We don't live in a perfect world, and this is really hard stuff to do. So the fact that it, boy, has a pretty decent trend on one-to-one, we're very satisfied with that. That's something that's going to be very useful to the operator. In what we're doing currently, we're coming at this from an improve operations perspective. We are not coming at this from let's make the best model possible perspective. Hopefully that makes sense. I come from a world where all models are wrong, some are useful. So this model is wrong, but it's useful and it's pretty correct in the world of modeling, right? So this one looks pretty good. And so the take home here is we can predict volatile solids concentration in minute by minute. Every minute, this system is making a prediction. So minute by minute, we can get that information into the operator's hands in the case of high strength waste. I mentioned earlier OLR, organic loading rate. Well, so the beauty of this facility is they've got then the flow rate that they are dosing the high strength waste. And so if we multiply the concentration that's being predicted by the flow rate that's being dosed, we can get the organic loading rate, which is mass per time, right? Mass per time. And so we observed the organic loading rate from January 15th to February 24th in this particular plot. So it's observed. It's really a combination of grab samples that have the concentration and then the flow rate. So it's a calculated observation. And one of the things we want to know is, hey, there's a typical loading rate. You got a range for that. At this particular facility, 1.6 kilograms of volatile solids per cubic meter of digester volume per day would be considered high. And so you can see some days where, boy, they're really tempting fate, right? They're tempting fate. They're above the green line in their organic loading rate. Had they had some real-time information, as our pilot study could have provided, maybe they wouldn't have done that. Alternatively, on these days where it's really low, right, it's not nestled up toward the high loading rate line, maybe they would have pumped a little faster. So to get their organic loading rate up, the idea behind this system is to quench the variability and then maximize that biogas production, all while then reducing that risk of catastrophic failure. So here, this is a combination of high strength waste and then the two sludges that are also being from the municipal facility itself that are also being dosed. And so we don't have real-time data for those two sludges, but those sludges are pretty constant, pretty consistent, and so we can assume what they are. What we did here, though, is we have the predicted high strength waste during that same time, and you can see that it's really the high strength waste that's creating that variability in the organic loading rate that digester is going to see. And so if we get this high strength waste prediction into the hands of the operators, they can make some decisions in real time that could be really beneficial. We also did this with, well, I should back up a little bit. So organic loading rate for volatile solids, again, that's just a bulk composition surrogate, volatile solids. It's also nice to be able to break that down into things like fat, carbohydrates, and protein. And so here we're showing you how the prediction works for fat. Again, a one-to-one plot over here on the right looks pretty good when those data points land on the one-to-one line. And then again, if you prefer to see it in a time series, there it is right there. We did it as well for carbohydrates. Look at those carbs, man. Look at that, R squared of 0.98. fantastic ability to predict those carbs. Protein, not so much. Protein here on the one-to-one line doesn't really follow that, that perfect match like you would want. There's a reason for that, and that's more in the analytical technique in the sense that typically when you send your sample out for protein analysis, they will reduce that sample into 100%, all the nitrogen into ammonia. And then they'll take that and multiply it by a magic number of like 6.25 with the assumption that all protein has 16% nitrogen in it. That really did a disservice for us. I should have known it was going to happen. I wish I would have thought of it, but we really need to know the specific protein account, which you can, or a protein composition. We can only do that by a full amino acid analysis rather than this very simplified protein analytical technique. Regardless, though, it's wrong. Yeah, the model is wrong, but it's still valuable in the sense that if we can predict protein in real time, that's where your ammonia in the system comes from. If you want to balance your carbon to nitrogen ratio, or if you want to avoid ammonia inhibition, you need to be able to know your protein loading in real time and make some adjustments as needed. We're working on that ability and can do that. As we transition now to the on the farm part of the story, I do want to remind you that this technique is not it's not new to a lot of farmers. I think Dan has this sensor, if I remember correctly, sold by John Deere, at least marketed by John Deere. It's made by a different company, but you can use this technique on grain, on feed, all sorts of different things for farm applications. Again, where you can get many of these same metrics I've been talking about: protein, sugar, which is carbohydrate, starch, carbohydrates, fiber. Again, protein over here, sugar, nitrogen. You can also predict ammonia nitrogen directly, which is nice to know in your digester itself, so on and so forth. So it's already on the farm, which is great for folks like me who don't work on the farm as much as someone like Dan. But as we start to experiment with it on the farm, it's just good to know that it's out there in one form, if not the same form that we're using it. And so Amana Farms. So I thought I'd share a little bit about Amana Farms itself. It's one of the largest contiguous farms in Iowa, 75 tons of manure per day, a 1.5 or 1.7 million gallon mesophilic plug flow anaerobic digester there. By the way, they also have hauled organics here. I'm calling them industrial organics. Biogas gets dehydrated before fueling up to 4 reciprocating engine generators. Part of the reason why I was brought onto this project is they've only been making enough biogas to routinely run like 2.5 of their generators. And so they're losing money because they can't run all 4. And so that's why I was brought on board to try to figure out ways that they could get more biogas. When you get the solids and the liquids that come out of the digester, they're used as fertilizer for farm fields at Amana. Their feedstock mixes are roughly 54% hauled organics, 29% manure, and roughly 17% settling pond supernatant. They bring that supernatant back to balance their carbon to nitrogen ratio to make sure that they've got what they need in the digester. Their slurry pit has a couple of piston pumps that feed the digester, and they put in roughly 50,000 gallons per day into the digester itself with that blend that I've shown above. And then again, that settling pond supernatant is used to reach a desired solids content and to balance carbon and nitrogen ratio. And then it's important to note too that fractions of the feedstock slurry are added along the length of the digester. So it's not really a true plug flow style digester. It's a bit of a modified design. If you want, you could just Google this, by the way, Amana Farms virtual tour anaerobic digestion on the farm conference video. It's about 9 minutes long. If you want to see that, it's a great product that Iowa State put together a couple falls ago. So this is what it looks like there. Now, what I've been showing you before was a very expensive Buki NIR sensor, about $100,000 each, that requires a pipe with something flowing through it. You put a $20,000 flange into that pipe. So now you're at $120,000 capital investment. And then you strap that, you bolt that sensor onto that flange. So it's quite invasive and it's quite expensive. What we wanted to explore at Amana Farms in this context is the use of this handheld unit, which we're showing right here. I don't know if you can see my cursor, but right here is a handheld unit that does all the same things in a much different footprint at a ridiculously different price point, about $10,000. It's not fully automated, but in a system like Amana Farms, they are doing hauled waste, they're doing co-digestion, but their feedstock blend doesn't change as violently as Muscatine, Iowa, WRF does. And so you can make a pretty compelling argument that a device like this, with just a couple, snapshots a day, could really go a long way toward helping the Amana Farm operation. So we took a sample from their slurry pit. You can see their slurry there in the background. Got a nice, yummy look at their slurry. I think it's mostly manure right now. They're just doing a digester clean out. They've never cleaned it in about 15 years. And so they're mostly dosing manure at the moment to get the thing up and running again. They'll start bringing their hauled waste later. And so we wanted to see how well this technique could work as just a quick snapshot at Amana Farms. And here we go again, the squiggly lines that we talked about. So what we did was we took that sample, brought it back to the lab and made a few dilutions on it. So we could essentially have like whatever, 75% strength, 50%, 25%. Again, just for proof of concept on whether or not this could work. And so you can see the changes in the amplitude. Some of these spectra are duplicates, replicates, I should say, of each other. You can see the change in amplitude. Ironically, the more dilute samples have a higher amplitude because water absorbs, right? Water has an impact on this spectrum. So the more water, the higher the amplitude you might have. So then we'd run this through, again, something called supervised machine learning, where we take some grab sample data associated with these squiggly lines, and we turn it into predictions. I have an instrument at our labs that can measure lipids or fats really quickly. And so we chose to do that parameter for a pilot study. And here's what that looks like. And so we've got the observed fat or lipid content on the x-axis, the predicted on the y. And you can see we get quite a lovely one-to-one plot there, which shows great promise for use of this technique on the farm. I also would like to see how this might be able to work with increasingly smaller digesters. Again, so we've got techniques that can be right-sized to the particular application at hand. So reflecting back on this upset digester just for a moment. So let's think about the future of this. Just got one more slide and we'll open it up to questions. So again, reflecting on solving this particular problem where we do not want this digester to get upset. What would a live system look like in that particular case? And so we've been experimenting with something I've recently been calling a digital apprentice. All right, so we got these machine learning models. That's great. You can turn squiggly lines into predictions. But if we just start blasting a bunch of predictions for, who knows, 20 parameters every minute to an operator, they still might not know what the heck to do. Should I pump in more feedstock? Should I pump in less? What should I do, right? It still doesn't really solve that problem where you're an operator in Muscatine, you got 10 other jobs you got to do, and you have to decide how to dose the feedstocks and what composition they should be. If you go out to Amana Farms, their operator, Colin Strickland, who's amazing, by the way, he's doing 1,000 other things as well, right? He can't just sit there at his desk all day and decide what to put in the digester that day. He's got a lot of other responsibilities. So how can we bring this technique to bear in both of those situations? So I'll tell you the way I'm thinking about it at the Muscatine Wharf. So we've got this sensor over here that gives every minute what I would consider lab data, right? You grab samples would be the standard. Sometimes those grab samples take hours or days to get results back on. So we get real-time lab data from this diffuse reflectance spectroscopy technique coupled with machine learning. In Muscatine, they have a bunch of other data. They've got hauled waste flow, they've got sludge flows, they've got all these pumping rates, I've got digester lid position, so on and so forth. We can bring all that together too, and then couple it with this real-time lab data, right? We can couple these things together. Now, what's called a level 4, some people would call this a digital twin. At the level 4 level, I would get this information in real time to John, but John Cook is the lead operator down in Muscatine. What I could do is have something on his phone that says, rather than just give him, here's your ammonia content, here's your volatile solids, here's your fat, carbs, and protein, and just blasting him with all these squiggly lines, time series, I could just say, hey, John, given your conditions right now, your high strength waste flow rate should be 35 gallons per minute. Then as an operator, you can decide whether you're going to change it or not. Maybe you're at 40 and you say, okay, I think the model is giving me a good recommendation. I'm going to knock it down to 35. Vice versa, maybe you're running at 20. Model says to run at 35. You can use your operator discretion on whether or not you want to change that pump speed to meet what the model is suggesting that you do. Of course, in the future, if you have a very dynamic facility like they have in Muscatine, you might imagine the digital apprentice would change the pump speed for you. The digital apprentice says, I think you should be running at 35 gallon per minute right now. You connect it directly to the pump and then it changes it. Of course, you got operator oversight of the operation, but that would really be the future where I'd like this to go. Whether or not that applies fully to a place like Amana, that's another thing altogether. But it certainly foreshadows what could be a possibility there, assuming it meets affordability and reliability requirements. So some key takeaways, can diffuse reflectance spectroscopy provide real-time composition monitoring? I think that's an emphatic yes. I will tell you, as a longtime analytical chemist and environmental engineer, I was very skeptical of this technique about 3 years ago when I first got into it. Today, I know it is quite valuable and useful in a variety of situations as long as you understand the uncertainty that's involved in the technique. Then the second question, can a digital apprentice for anaerobic co-digestion be implemented at full scale? I think, yes, it can. We did that for a little while at Muscatine, although a brief moment. And then can diffuse reflectance spectroscopy and a digital apprentice together be used for what I would call semi-autonomous operation at full scale? And that is to be determined. And so with that, I would love to take any of your questions.
First off, thank you so much, Craig. That was amazing. I think Melissa is going to give anyone who wants to verbally ask their question the ability to unmute now. So if you would like to unmute and ask a question, feel free. Otherwise, Luke Soko asked, what machine learning method and software was used?
Yeah, great question. So this is a pretty simple machine learning algorithm based on partial least squares, so just a PLS. And this started for me in some Python, so it's all Python. So we have this script running in Python on the local machine. Actually, all these predictions are run on the local PC. We actually do have a live cloud connection. We can move it all around to phones or wherever you'd like it to be. But it's there. What we've learned, though, about this technique, it's all in the pre-processing, I guess, algorithms, or methods that you would use for this as well. And there's a variety of things we've tried with that, and I'd be happy to provide some more details on that. We've actually got a full manuscript on this project that I just got last night from my PhD student, and that has some more of those details. I'll be happy to share that, and also a variety of other things that we've been doing to make those models better. But at the core of your question is partial least squares. Pretty simple in the context of machine learning models.
And then I'm going to steal the next question. How'd your operators at the Muscatine plant feel about it? I mean, it looked super successful to me, but I feel like an operator at first would have been pretty skeptical.
Yeah, well, and first and foremost, McLean Putney is in my group. He's staff. He is a grade 4 wastewater operator, licensed in Iowa. He worked at the Iowa City plant for 5 years. So sending him on site, built, and he would bring donuts frequently. And so that built a lot of rapport with the operators. What I would say is this didn't really get to the it didn't really get beyond John Cook, the lead operator. John Cook is an experimentalist. He loves trying new things. It really stayed with him. And we, again, as I alluded to, we only had this full fledged pilot where I could see real time stuff on my phone going for about 2 weeks. And so, really, all we could do is just imagine its potential after we built it. And that was really the goal of this project. Getting that operator buy-in, it would have to be way more resilient and robust, and we would have to have done a lot more, testing on our own to ever really put it in front of that audience. So to be determined there as
Okay.
well, Jim.
Again, if you have questions, feel free to put them in the chat. Otherwise, I'm going to keep stealing the opportunity to ask questions. So when you think about Muscatine versus Amana, Muscatine sort of gets whatever's in the area and they have to take, I imagine. There's little choice to say no. But on farm digesters, you're sort of screening different substrates and then often signing a contract to take them. What's sort of the potential for using NIR as a tool to help pre-screen and make some preliminary decisions on, am I even interested in taking this?
Yeah, I know Amana Farms in particular, they don't have any ability to do hydrogen sulfide scrubbing, for example. And so they, by default, on any potential new feedstock that they're not very familiar with, will send it out for a sulfur content analysis because they only want low sulfur feedstocks. And to your point, they are typically getting a relatively long-term contract for something that's also relatively known. And so if that's the case, it may not really be that valuable to evaluate a feedstock with this technique because the other thing, again, all of these sensors need to be the sensors give you squiggly lines, and then the predictions are only as good as the training data that you feed the machine, the supervised machine learning model. And so often that training is substrate specific.
Mm.
And so you could get a brand new thing that you want to evaluate. You might not have a good model for it. You could aim your sensor at it, get a prediction that might not be satisfying. So I don't really think that to me isn't the use case for it. The use case for me is if a Amana wants to run all four of their generators and they need to get every bit of biomethane per day generated, that means they may want to run up against an operational boundary where they'll be at more risk of upset. So to me, being able to take a snapshot of that 50,000 gallons of slurry they made that particular day, because they do get some variability in their hauled wastes. Even under these contracts, they show up at different times. Some show up every 2 weeks, some show up twice per week, so on and so forth. So there is a bit of variability in the blend they would make each day, and it's a bit of artistry with respect to deciding, how much to dose on any given day. If we could give them that ability to do a snapshot on relatively known feedstocks within kind of a matrix of known feedstocks, then they could make some better decisions and perhaps again get that more maximized biomethane production, and then again minimize their risk of foaming and or just catastrophic failure.
Mhm. Yeah, even on your Muscatine graph, you said 1.6 was maybe a high rate, but they spent a lot of time down at 1.2. Like there was a
Exactly.
lot of,
Exactly. Yeah, if you get some of this Kraft nacho cheese, you get 3 or 4 pallets of that stuff. You open up those, nuclear orange cans, starting to think about putting that in your digester, you could misfire on that pretty easily. And so you might then say, hey, I'm going to load this in really slow. Well, you might be too cautious. just because it's such a, kind of a crazy feedstock. And so, yeah, the idea is to, yep, here's a snapshot, dose in confidence, based on what the models might suggest for you.
All right. Last chance for questions, everyone.
Any others?
Luke sort of wants to know how long is high strength waste stored before input in the digester, and what sort of VS losses do you have during storage?
Yeah, great question. So, if you go to the video on Amana Farms, you'll see their storage system, which is roughly 8 vertical tanks that, they'd be almost like you would have at a gas station that would be buried underground, or sometimes you'll see those holding fuel at like a farm service, like a cooperative or what out in rural Iowa. Those tanks, I don't know if those are 50,000 gallons or something like that. They've got an ability to store those things for quite some time. The overall length of time, to your point, they are somewhat enclosed. I don't think they're stored for months and months. It could be weeks and weeks. And then in the case of muscatine, at least things are, in the nacho cheese can, or, if it's in the form of dog biscuits, for example, that's not very volatile. If it's in the form of Oscar Mayer sausage, probably not much going to happen with that. And so until they take that out of that container, it's probably pretty stable in that sense. So I don't know that there's very much loss of that, because that would really create a lot of smell issues and things like that. And both of these places have their odors, but it's manageable in many ways. So I think they've got a pretty good control on that overall.
That's a great point. I think storing of that stuff is vastly different than maybe storing a manure where it comes with the microbial inoculum attached.
Exactly. Exactly. Yeah. These things, I think they're meant to, that's why you don't want to put them in they're somewhat biodegradable, I guess. Man, I don't know how many digesters see nacho cheese very often and try to adapt to that. But yes, they're pretty stable until you open them and then get them in the digester.
And then could you just comment at all about that can processing? How well do those systems work at separating out maybe some of the packaging material compared to the organics that we want? Is it pretty clean?
No, not really. Well, I mean, it's relatively clean, but one of the projects our senior design students did a year and a half ago, maybe, was evaluating how to add a plastics, a micro, not even really micro, they're macro plastics that get into the digester, because those plastics get ground up, and yeah, only the big stuff ends up in the hopper that goes to the landfill. There's some pretty good sized plastics and other materials that end up in that high strength waste that goes right in the digester. And you can see it plain as day in the digestate. And so that's a liability to this approach. And then, of course, if you can imagine, we're in the PFAS era right now, too. You bring in hauled waste, and that hauled waste just happened to have, forever chemicals, PFAS or otherwise. Someone gets wind of that, and you do an analysis and you show that you're putting that on farm fields as digestate. Boy, you've got an issue there too. So there's a variety of risks, even beyond kind of digester upset, that come into play here if you're going to do this hauled organics, co-digestion approach.
Perfect. Capel.
I got a quick question. Knowing the variability on chain stocks going into that muscatine digester, um, what design changes would you think or suggest for a digester like that?
Yeah, great question. So, muscatine doesn't have very much storage capacity. They could use a lot more. So that would be one. And by the way, muscatine had a full design prepared to like roughly a 30% design, to really build, their facility of their dreams. So they also don't have a great ability to offtake stuff that comes as a liquid. So what I showed you with that big machine, that just depackages things. In another image, I showed you a tanker truck. That's already in liquid form. It doesn't come in a package. And so they can dump that in directly. Well, they don't have a very good system for offloading those types of waste, so on and so forth. So Muscatine could use a lot more storage, better way to offtake, so on and so forth. If you go to the Des Moines Water Reclamation Authority, Des Moines Metro is huge. Their facility is massive. They're doing anaerobic co-digestion at a very large scale, and they've got official places where trucks weigh in. They can offload liquids in an amazing way, and it's so much more, um, automated and things like that. Muscatine's up and coming. They're a pretty small facility, and they don't have all of that. So those are some of the major things that if I could, I would redo. One of the things Muscatine has, though, is that amazing industrial depackaging facility. And one of the things they've talked about is actually being a broker of organics for other facilities. Because, for example, the city of Iowa City is looking to do anaerobic co-digestion. They've got a bunch of digester capacity here in town that as wastewater treatments become more efficient over the years, they don't need all those digesters anymore. And so they're looking at bringing in hauled organics, but they don't really have enough seemingly in the Iowa City area. We don't have a lot of food processing industries, things like that in the local area. And so they might even work with the city of Muscatine to have some of their depackaged organics come to Iowa City. Iowa City, I've seen their preliminary design, and they do have, again, storage. They've got a way to remove plastics that end up in the digestate, so on and so forth. Those would be some of the main things that you'd want to have in a facility if you had the funds and we're going to kind of build it from scratch.
Perfect. Thanks, Craig. And now I'm going to do some housekeeping. So, our next webinar is on September 9th, and Carly Lewis from Livestock Water Recycling is going to be talking about Beyond Biogas, the science of post-digestion treatment. Another one I'm super excited about. So, they will go through their system, which includes all the way to making clean water that's dischargeable at the end. So, as we think about scaling some of these digester facilities at a farm, we might have to think about more than land application in some cases. So, super excited about that. If you are interested in watching any of our past webinar series, you can find them on our YouTube channel shown above. And I didn't tell Craig this, but we do try and share slides. So I'll see if he's willing to send us a PDF copy and get those posted on the box. He is, so we'll get that posted. It normally takes us a couple days to get the transcripts written up from what we all said, depending on how talkative we are and how well AI works at figuring out the words that are sometimes a little specialized. So it might be a day or two, but we will get those up if there's someone you want to share this with. And then we do have an anaerobic newsletter. So if you're interested in the newsletter, if you're not watching this on your phone and want to scan the screen now, I'm supposed to stay long enough that you can scan that QR code and it will take you to a web link and get you signed up. So we'll keep you updated on where we stand with the webinar series. And that should be all I have. So with that, once again, big thanks to Craig. I thought that was a great presentation. I learned a lot about potential for real-time monitoring, and it looks like some exciting opportunities to make management a little bit easier. And thanks everyone else for joining us today.